In this module, we will consider conservation of energy and power. The work done on an object by various forces can be grouped into the net work done by conservative forces and the net work done by all other forces. These other forces could be things like specific contact forces, such as you pushing on a block, or friction, or mass energy transfer into or out of a system. And for more complicated systems where we deal with collections of particles as real solid objects, we may have to consider heat and other internal energies. But in general, we can divide the work into the work done by conservative forces and the work done by all other non-conservative forces. And by the work kinetic energy theorem, the sum of these will be equal to the change in the total kinetic energy. Now, because the work done by conservative forces can be written as minus the change in the potential energy, then we can obtain the very useful equation that the work done by all non-conservative forces is equal to the change in the kinetic energy plus the change in the potential energy of the system. In the special case where there are no non-conservative forces acting so that work other is zero, then we have what is called an isolated system, where the energy is not transferred out of the system or transformed into possibly unrecoverable internal energies. So in this case, the change in the kinetic energy plus the change in the potential energy will vanish. And we can define something called the mechanical energy of the system, denoted by the letter E, which is equal to the kinetic energy plus the potential energy. We see then that a simple isolated system conserves mechanical energy, that is, the change in the mechanical energy will vanish. However, for a general system, the change in the mechanical energy is going to be equal to the work done by other or non-conservative forces acting on objects in the system. We find that for isolated systems, mechanical energy is conserved. If the potential energy of a particle decreases, its kinetic energy increases by the same amount. Similarly, an increase in the potential energy of a particle comes from a decrease in its kinetic energy. Because kinetic energy depends only on the speed of the particle and potential energy only on the position of the particle, if we know the mechanical energy, then if we know the position of a particle, we know its speed, and if we know the speed of a particle, we know its position. So consider the following example. Let a particle of mass m slide without friction on a track as shaped in the figure. What are the speeds of the particle at position P1 and position P2 if released from rest at the top of the track? First of all, if we try to solve this problem using standard Newtonian mechanical techniques, F equals ma, this would be a very difficult problem to solve. The reason is that in addition to the gravitational force acting, there's also a varying normal force acting on the particle. As the particle moves along the track, the direction of the normal force is going to change and its magnitude will change, and it will depend not only on the position but also on the speed of the particle because it's going along curved paths, and there will be centripetal accelerations which have to be created by normal forces, and it just gets very, very complicated. We have a varying force, which means we have a non-constant acceleration acting on the particle, and it's just a difficult problem to solve. However, if we use conservation of energy techniques, this problem can be solved in a very straightforward manner. Now, first of all, we have to realize that the normal force, which we said was acting on the particle, does no work. Remember, the particle is moving along the track, but the normal force is directed perpendicular to the direction of the track. And so, because the particle moves perpendicular to the normal force does no work on the particle. Because there are no non-conservative forces acting, we have an isolated system and energy is conserved. So the total mechanical energy of the system will remain constant for all points in the motion of the particle along the track. So we can calculate this mechanical energy at any point in the particle's motion along the track. Consider its initial position. In this case, the total mechanical energy of the system is just the sum of the kinetic energy plus the potential energy. The object starts at rest at the top of the track, so the kinetic energy vanishes. It's at a height of 2h, and so it has a potential energy of 2 mgh, and that is the total mechanical energy of the system. As the object moves towards point 1 along the track, it will now have some kinetic energy, and we know the potential energy at this position on the track. It's simply mgh. And so by conservation of energy, we can say that the energy initially is equal to the energy at E1, and that gives us that the speed at position 1 is given by the square root of 2gh. Now, it's important to remember that this is not simply the velocity of the particle that it gets from falling freely in the vertical direction. This is the speed of the particle at this point on the track. The direction of the velocity is going to be along the direction of motion along the track. If we then consider what happens when the particle moves to position 2, well, once again, we can do the same thing. We can find that the kinetic energy is going to be 1/2 mv2 squared. We don't know this yet, but we do know the potential energy. It's going to be mg times the zero height where the particle is now. And we can once again use this to solve for the speed at this position. And this is the square root of 4gh. Again, the direction of this velocity is going to be tangential to the track here. Now, one thing is important to consider at position P1. Because the track is curved here, there is a need for a centripetal force to cause the particle to curve along with the track. This centripetal force must be caused by gravity. So in a case like this, to be careful, we would need to go and check to make sure that the component of gravity in the direction perpendicular to the direction of the track is sufficient, given the speed of the particle, to provide the centripetal force necessary to keep the particle moving along the track. Another very important concept we want to mention briefly is power. Power is the rate at which work is done. So, for example, average power can be defined as the amount of work done divided by the time interval during which this work is done. That ratio would give you the average power exerted during a given time. Instantaneous power is simply the time derivative of work. Now, since an infinitesimal amount of work is equal to the force dotted with the direction of an infinitesimal displacement, we can replace this and see that we can also write power as the dot product of force with velocity. This turns out to be a very useful way of computing the power expended by some object. Also, the units for power are simply going to be energy divided by time, that is joules per second, which we can write in basic units as kilogram meter squared per second cubed. And because we use this unit so often, we give it its own name. We call it the watt and designate it with the letter capital W. So this is the SI unit of power.